Section 7.3 looks at another transcendental function called the logarithmic function. Now, the definition of a log is basically it's the inverse of an exponential function. Now, if you'll remember when we did inverses before, the steps that we used to find the inverse was we let f of x equal to y, we switched x and y, and then we were supposed to be able to solve for y. Notice we cannot solve for y here. There is nothing that we can do that will undo this so that we can get y by itself. So they just actually named the inverse a logarithmic, and they gave us a definition for the log. And a common log would be something like this. Y is equal to log base 2 of x. And it is the inverse of the exponential function 2 to the x power. Now, let's talk a little more about our logs. Back in the day, when I was in school, which was long before y'all were born, we worked logs using tables out of the back of our book. They no longer have those tables because we now have calculators. On your calculator, you should find two buttons. The first button, LOG, is for the common log. The common log has a base of 10. So anytime you see just the word log and a number out to the side, you would use your log button and find those values. So using your calculator, you should agree that the log of 1,000 is 3, the log of 350 is 2.54, the log of 1 over 100 is negative 2, and the log of 85.67 is 1.93. Now there's also another button on your calculator which is the natural log, and it would be the LN button on your calculator. And again, this is a special log that has a base of E. E is a non-terminating, non-repeating decimal. It's approximately 2.718. And again, the calculator can do this work for you. So typing in the natural log of 8, you should agree it's 2.08. The natural log of 35 is 3.56. The natural log of the cube root of E, now if you do not know what the cube root is, remember that's the same thing as the 1/3 power, so you could type it in either way in your calculator, but you should get 0.33 repeated. And then the natural log of 4.78 would be 1.56. Now everything's great as long as you're using a common log or a natural log. But if you were to get a problem that has a completely different base, something other than 10 and E, you're going to have to use what we call the change of base formula to change it to either a common or natural log so that you can use your calculator. Notice what the change of base formula says. If you want to take the log of some base of x, you can change it to any base you want, but we want to change it to a base that we can use our calculator on. So we're going to change it to a common log, a base of 10, or a natural log with the base of E. You do this by taking the log of your new base of x and dividing it by the log of the new base of B. So if I was to use the common log for this first example, I would type in my calculator the log of 6 divided by the log of 4. Now you could have done the exact same thing with the natural log. It would have been the natural log of 6 divided by the natural log of 4. And then your calculator would be able to work it for you, and you would get 1.29. The next one, log base 5 of 80. The base is 5. We can't use our calculator unless we change it. So I'm going to rewrite it as the log of 80 divided by the log of 5, which would give you 2.72. This third one, log base 3 of 81. Again, the base is not the common log or the natural log, so we've got to rewrite it. So this would be the log of 81 divided by the log of 3, which is 4. And then one more, the log base 7 of 760. We would rewrite it as the log of 760 divided by the log of 7, and that would give us 3.41. So, if you have a common log or a natural log, you pick up your calculator, everything's great. If you have a log that has a base other than 10 or e, you've got to use this change of base formula so your calculator can still find you the answer. Now, we said that these logs are inverses of an exponential function, but we could not follow our algebraic steps to get from one to the other. So there's got to be a way that we can convert one to the other. And here's our rule. If we had the log base a of x equal to y, that would be the same thing as a to the y is equal to x. So for the next couple of problems, we need to practice on rewriting from an exponent to a log and then a log to an exponent. Now, the easiest way for my students in class to see this is they remember that the base of the log is the same as the base of the exponent. So once they've got that down, they know that number is going to be the same. If you'll look at the exponent form, the exponent is the y, which if you go back and look at the log form, that is always going to be on the other side of the equal sign. Alright, so rewriting this, we have 625 is equal to 5 to the 4th. Alright, first off, we know the base of our exponent is going to be 5. And remember we said the exponent would always be on the other side of the equal sign, so that would give us that this is the log base 5 of 625 is equal to 4. Now remember, we're not doing anything but rewriting. We're not trying to solve these or work them out. So this next one, this would be the log base 4. Again, the exponent goes on the other side. So it would be the log base 4 of 31 is equal to x. This third one, the log base 16, exponent goes on the other side. So we'd have the log base 16 of 215 is equal to 2x. And then one more, we would have the log of base e, exponent on the other side, of 20.86. Now, you do need to take one additional step here to rewrite this. Remember we said if it's the log of base e, we call that the natural log. So this would be the natural log of 20.086 is equal to 3. Now let's go the other way. If I have a log, let's see if we can write it as an exponent. And again, we are not trying to solve this, we're just rewriting. So again, we locate the base. Remember the exponent's on the other side. So we would have 2 to the negative third is equal to 1 over 8. This next one, my base is 5 to the d power would be equal to 8. Now this third one, if you'll notice, we do not have a base written, but it's the natural log. And if you'll remember, the natural log is understood to be a base of e. Now they're not going to write that. You might want to, but you've got to remember the natural log is a base of e. So when we rewrite this, it'd be e to the second power is equal to 6x. And then this last one, again, there's no base, but it's log, so that's the common log. That means that the base is understood to be a 10. If you take that base to the exponent, we would get 10 to the negative 3 is equal to 1 over 1,000. So we've looked at how to find the value of a log function. We've talked about the change of the base formula, and we've talked about how to go back and forth between a log and an exponent. We do need to look at how to graph these logs. Now, remember we said it's the inverse of an exponential function, and one of the characteristics of an inverse that we had on our last test is that their ordered pairs are swapped. So if you'll remember, when we did the graph of 2 to the x, we put in a couple of negatives, 0, and a couple of positives, and we got 0.25, 0.5, 1, 2, and 4. Now, if we were to use that t-chart, recognizing that they are inverses, that would mean the t-chart for our log would be 0.25 and negative 2, 0.5 and negative 1, 1 and 0, 2 and 1, and 4 and 2 by swapping our x and y values. So using that to graph, 0.25 is very small, negative 2, 0.5, negative 1, 1, 0, 2, 1, and 4, 2, connecting the dots, that would give us our general shape of our graph. And just like we had before, the graph of the inverse and its function are symmetrical over that 45-degree line. Now, we know how to evaluate our logs with a calculator, but sometimes the logs are easy enough that we're not going to need a calculator. Remembering the fact that the log function is nothing more than the inverse of the exponential function, we can basically just ask ourselves what exponent we can raise each base to get the value that's given. So for this first one, log base 6 of 36, you most definitely could do the change of base formula, but if you'll just think about it, 6 to what power is equal to 36? That is 2. The next one, log base 4 of 64, what exponent of 4 would give us 64? That would be 3. The third one, log base 2 of 1 over 16. Now you might have to think about this for just a second. 2 to the 4th power is 16, but we want it to be 1 over 16. That means we want to flip it, so it has to be an exponent of negative 4. And then the last one, log of base of 2/3 of 8 over 27. Again, we're trying to figure out what exponent of 2/3 would make it 8 over 27, and that would be 3. Now, these properties of logs you will want to have memorized because you will run across them, and if you have them memorized, then they are much easier to work with. If you forget them, though, you can always rewrite the log as an exponent, and you would come up with the correct values. But if you had them memorized, it would be much quicker for you. Alright, so using the way to rewrite our logs as an exponent is one of the ways that we can use to solve our log equations. If you'll look at this first one, if I rewrite this as an exponent, it'd be 6 to the negative 1 is equal to 2x. I should be able to solve that from here. Negative exponent means to flip. To solve, I'm going to get rid of fractions by multiplying by the least common denominator, which is 6. Last step is to divide, so x would be 1 over 12. This next one, if I rewrite it as an exponent, I get 2 to the 5th is equal to 8 to the x. But now if you'll notice, we now have created us an exponential function. We need to get those bases the same. Well, the 2 cannot be rewritten. The 8, though, is 2 to the 3rd, and we still have an exponent of x. If our bases are the same, the exponents are the same. Dividing by 3, we would get x is 5/3. Log base 16 of x is equal to negative 3/4. Rewriting this, it'd be 16 to the negative 3/4 is equal to x. Remembering what the negative 3/4 power does, that's going to flip it. It's going to be the 4th root, and it's going to be to the 3rd power. Now the 4th root of 1 is 1. The 4th root of 16 is 2. We still have to cube that. 1 cubed is 1, 2 cubed is 8, so our answer would be 1 over 8. This next one, rewriting it, we would have 5 to the 2nd is equal to 5 to the log base 3 of x. If you'll go back and look at the properties that I told you to have memorized, if the bases are the same, the exponents are the same, but that's created a log equation, so another log equation, so we'll rewrite again, and we would get x is equal to 9.